Okay, why don't we get started? So today we're going to segue topics and spend the bulk of today talking about neural networks. And so where we last left off, we talked about the likelihood function in logistic regression, and we made use of monotonic transformations to put this likelihood function in a form that looks like in-sample error. And we called that pointwise error so-called cross entropy error. And it was a measure of coincidence between the ground truth, so-called target probability, and the hypothesis in terms of the way probability mass is assigned associated with each one of the input vectors, how probability mass is assigned for the +1 versus -1 alternatives. And so we had the logistic regression algorithm where we compute the gradient by taking the derivative of En, and then we update the weights some step size nu, eta, no, eta, um, where that update to the weight vector scales so that the larger the gradient, the larger the jump. And as you get closer and closer towards the minimum in that error function, that step gets smaller and smaller and smaller as you walk down the basin of attraction. Okay, and so we ended last time with this description of all the linear models and the relationships they had with one another in the context of the credit approval problem. And we highlighted that by changing various aspects, namely the pointwise error, as well as the algorithm, as well as the threshold, whether it's a soft threshold or hard threshold, we can dramatically change the behavior of what we originally thought was a very simple, not very capable linear model, but just by changing various aspects of our anatomy of a learner, we can get pretty different types of and more sophisticated types of behavior out of our simple linear model. And so the linear model is a great building block. And we will revisit linear model when we talk about kernels and support vector machines to add a little bit more formalism to this idea of a phi function. Okay, any questions about that? Yes, sure. This one? Mm-hmm. Yes. Yes, and this is over the gradient of En. This expression is the gradient of En, and you'll see there that summation. It's over all of the in-sample points. Okay. One whole pass through. So the gradient of En is defined over the entire set of in-sample points. So you compute the gradient of En, and then you update the weight vector, and then you compute the gradient of En, and then you update the weight vector. But when you compute the gradient of En, that's over all of the in-sample points. Okay? All right. Any other questions? No? All right. Good. Okay. So let's go forward with a little bit more about stochastic gradient because neural networks use stochastic gradient as one of the training regimes. And so gradient descent minimizes the convex error function. And recall when we talked about in-sample error, that was the average pointwise error over your in-sample set of data points. Now, of course, for logistic regression, when we talked about gradient descent, our pointwise error is cross entropy error, right? And so that pointwise error can be different things. In the case of logistic regression, it's cross entropy error. So there's our expression for in-sample error. And we iterate in steps along the gradient from one pass through the whole data set to the next. We iterate through our weight updates, some update eta, some proportion relative to the gradient magnitude of in-sample error. Okay, and so in the logistic regression algorithm that we covered last time when we just saw the slide, this is computed from all the samples from your set of in-sample points, right? And this is often called batch mode for gradient descent. It's called batch mode, excuse me, excuse me, it's called batch mode because you're computing this gradient of En over the entire batch of data, your in-sample points. But you don't have to do it that way, right? You can do it on a single point stochastically, and when you do that, you get so-called stochastic gradient descent. And so with stochastic gradient descent, what you're doing is instead of calculating the gradient of En over all the in-sample points, as we saw with the algorithm for logistic regression, you're calculating that gradient with respect to each point-wise error, i.e. the error on one single data point from your in-sample points at a time, and updating the weight vector relative to point-wise error. And now how you select that point, you randomize. And so you randomly select an in-sample point, you compute the point-wise error, compute the gradient of En with respect to that point, and then do the update. And then you randomly select another data point, compute the point-wise error using cross-entropy error, and then compute the gradient with respect to that error. And so instead of the gradient of En, what we're doing in stochastic gradient descent is our iterations, it's a large number of iterations, each time selecting a data point, and we're really computing the gradient with respect to our point-wise error, the gradient of little e. Does it make sense? And so if we do this enough times, well, in expectation, if you compute the gradient with respect to point-wise error for in-sample error, you get total in-sample error on average, right? Does that make sense? Any questions? And so this stochastic gradient descent has some desirable properties. Some of those properties are as follows. It's, for one, cheaper to compute. Instead of batch mode over 1,000 data points in sample or 100,000, you're doing it one point at a time, and it's also randomized. And because it's randomized, it exhibits some of those properties we talked about when we talked about these multi-dimensional surfaces. You can get stuck in local minima. It kind of adds this idea of noise, if you will, where you're less apt to get stuck in local minima because the sheer nature that it's randomized means that you're likely to escape these local minima because you're randomly selecting that point with which to compute the gradient on the point-wise error. And so the rule of thumb is, okay, you make it a relatively small step size, like eta 0.1, and certainly we said cross-entropy error is convex, and that convexity has some nice properties in that it doesn't matter where you initialize it, you're going to find the global minimum. But what is typical is more an error surface like what's depicted there on the right hand frame. And so you have some peaks and valleys, and you initialize someplace. And if you're taking regular gradient descent, you're more likely to get stuck in a local minima because you're looking at the gradient getting smaller and smaller and smaller. Your updates get smaller and smaller and smaller. If you're randomizing, it's very likely that you're going to jump out of that local minimum. And in expectation, it's going to give you the same as batch mode gradient with respect to in-sample error, but you also get this nice quality that has the ability to jump out of these local minima. Okay? And so this stochastic gradient descent is another way of performing gradient descent, but instead of calculating En with respect to the entire big N many data points, you're running some number of iterations, conceivably large number, but you're running some number of iterations where you're performing that gradient with respect to single point-wise error. Okay? So you get with stochastic gradient descent, you get the benefits of gradient of En in batch mode with enough iterations, but you also have benefits of this ability of cheaper to compute. It's randomized, which gives you the ability to escape local minima. And it's also very simple. Any questions about this? Does that make sense? Okay, so the Netflix prize. Now, the Netflix prize, it's already been won and claimed, but the Netflix prize uses a variation on stochastic gradient descent. And you could actually implement this and you'd do okay. You wouldn't win it, or it's already been won. But one of the things you could do to kind of go back to very early in the semester, the Netflix prize was an open competition to see if you could improve upon the prediction of ratings between that users would have for movies on Netflix. And so if you could improve on the system that was built by Netflix by more than 10%, the winner would get $1 million. And so this was claimed. And so in this, you have a vector representing a user, and each variable or each feature would represent some aspect of the content. Is it an action adventure? Does it have certain actors and actresses and so forth? And the more of that type of content a movie has, the bigger that weight depicted here by the size of the circle in each one of those positions. So for the user vector, these represent the preferences of the user for various aspects of the movie. And for the movie vector, these features represent the amount of content of that movie corresponding to these various measures or features. And so we have a user I, the U vector, and we have a movie J, the V vector. And so the idea then is that we have a database of movies and a database of users, and we have existing ratings, right? These are real ratings that people have had for movies in Netflix's system. And, recall it's very hundreds of millions of people that subscribe to Netflix. So it's a lot of data that they have. And so we have a rating Rij, is the rating that user I has ascribed to movie J, right? Now, certainly, if the contents of the movie very closely coincides to your preference, you're going to give it a high rating, right? And conversely, if the contents of the movie do not coincide very well with what your preference is, you're going to rate it very low. Let me just Yeah, it's still recording. Okay. All right. Because I couldn't remember if I said record. All right. I'm sorry. Let me continue. So this rating is an encoding of whether or not the user preference coincides or the user likes the movie, right? Okay. And so what they would do is they would take pointwise error and they would look at the coincidence between the user and the movie, and they would compare that to the actual rating for that user and that movie. And so the idea then is that it would learn what combinations or types of coincidences lead to certain types of ratings. And so in this, we have a pointwise error, and they use stochastic gradient descent, some implementations that you could do quite well with, to in a logistic regression model to predict whether or not did they coincide? Yes, did they like it, or do they not like it? And you would look at the difference between the actual rating Rij and the current rating associated with that user and that movie. And so in an algorithm, you could then engineer, if you will, what type of user is going to like what type of movie by just making adjustments to suit based on its coincidence, if you will, with the existing set of ratings. So then the hope is that you could take a new user and take a new movie and then build a system that you can use to predict the probability that a particular user is going to like a particular movie, or even just predict the rating itself. Okay? And so stochastic gradient descent works really well when you have lots of data, but the number of iterations is a key consideration that you would have to take into account. How many iterations are you going to run for each one of these pointwise errors to do that partial gradient? Okay? All right. So let's take a look at neural networks. And neural networks use stochastic gradient descent in training. And so a neural network is a type of model that's a so-called bio-inspired model. And bio-inspired, as the name implies, it takes its inspiration from biological system. Now, of course, in a bio-inspired model, one of the key considerations is something called biofidelity. How closely does your artificial system mimic the biology? Now, of course, you could have it mimic at the cellular level. You could have it mimic at the atomic particle level. That's a little bit overkill. Or you could just have it mimic in terms of its basic function or basic structure. Excuse me. And in the case of neural networks, on the left-hand side, we have an actual sheet here of neurons, and it's imaged under a microscope, and you can actually see the neural bodies, the axons and the dendrites, these neural connections that extend out, and they connect to other neurons. And through these interconnections, these synapses, when you have a voltage potential on one, it propagates down this arm, the dendrite, and then it excites the nearby neuron that's connected to it, and you have pathways of computation. Now, of course, in the computational abstraction of that, they made use of the structure, and the structure corresponds to some function that you're going to compute, and the arms, the little hairs that extend out, fingers, the dendrites that extend out. Uh, um, these are associated with weights, and in a real neural network, these weights are associated with something akin to resistance, and it can either inhibit or allow the excitation of the neuron to which it connects based on the so-called strength of the synapse. But in the case of the computational count, well, rather than simulating sodium potassium channels and ions and propagation, they just look at the connectivity and the weights associated with each one of these edges in the neural network. And so this bio-inspired approach to computation, it kind of stops very short and doesn't try to mimic all aspects of a neuron in its biological form, but it does perform some very useful computation. And you've probably heard the term deep learning before. Deep learning is very popular right now, and neural networks have enjoyed a sort of renaissance in machine learning due to two major factors. Well, three. One is an abundance of a large amount of data. There's a lot of sensor data. Two is some breakthroughs in architecture, specifically GPU computing. You can have some very high performance matrix operations on a large scale in a very small form factor. And the other is some very clever extensions on how you train these things. And so all three of those combined are so-called deep networks. So the networks are bigger and wider, and as such have a lot more parameters. And as we learned when we talked about learning theory and VC dimension, the more parameters you have, the more effective parameters you have, the more data you need. And so having a lot of data available, abundant data, makes this all very possible. And so deep learning networks have had a lot of wins, in particular natural language processing, in computer vision, in audio and speech processing. And one of the interesting things about it, the same algorithm back propagation can be used to learn regardless of the type of input, whether your input is images, whether it's audio, whether it's text, or what have you. And so deep learning, there's a lot of excitement about it. And as time permits for this class, maybe we will go beyond just neural networks and look at deep learning. So we'll see how the schedule plays out. We're at the halfway point for the semester right after spring break. Next week is spring break. And so we'll see how the schedule goes when I recalculate it. Okay. But nonetheless, regardless, I plan when we're at the 2/3 point in the semester, we're going to pivot to reading the research literature and now look at how these various aspects and considerations of a learning system, what choices people have made in the literature for this, and try to cast that in terms of the anatomy of a learner that we studied. Okay, so the idea of a neural network combines perceptrons, and this is perceptron with a hard threshold. And here in the frame on top on the left, on your left, we have a perceptron H1. And so we have an input feature vector in 2 dimensions. And we see that things in the perceptron beneath the line in the plane gets a +1, and things above the line gets a -1. So this perceptron implements a concept, if you will, where it can assign +1, -1 labels for inputs that are in this 2-dimensional representation. Likewise, we have another hypothesis, H2, and that's also a perceptron, a 2D perceptron, a line on the plane. and it can categorize or classify concepts as +1 or -1, where on the underside of this perceptron, it'll categorize all points on the plane, data points, as -1, and things that are up and to the right in this feature space, it's going to categorize as +1. And certainly, we can take H1 and we can take H2 and we can combine them. And if we combine them, we can categorize an arrangement or the geometry of points arranged in the following fashion. And so here we have H1 and we have H2, we combine them, and now we can categorize something that's a little bit more sophisticated, right? We can have their space carved up into regions so that the +1 points are up above or down below, and the -1 points are to the left and to the right. And that concept or that arrangement of points and their respective labels is much more complex than the individual H1 and the individual H2. And so how might we do this? Well, we might say, okay, everything that's in the minus region is categorized by H1 returns a -1, and at the same time, H2 returns a -1. Everything that's a plus is maybe H1 and H2 at the same time return a +1. And so you can certainly combine hypotheses, and one way to combine perceptrons is using a logical and or logical or function. And so thinking of the perceptron, again, as sine W transpose X, if that signal S W transpose X is greater than 0, it returns a +1. If it's less than 0, it's negative, it returns a -1. And so let's think about what an OR means. OR says that one of them or both of them are positive, are +1, or a logical 1, if you want to call it that, and it'll return a 1, right? If both of them are 0, it returns a 0. So at least one of them has to be 1 in order for it to return a 1, right? Okay, so let's see what happens here with the OR function. It's late. You get me at the 4:30. Let me start. It should be +1 and -1. Okay, it should be +1 and -1. All right, let's start over again. And I'll cut all this out the video. So we have the OR. OR says, are they both +1, right? They both have to be +1 for the OR to return +1. They can be +1 or -1. If x1 and x2 are both +1, well, +1 plus +1, that's +2, and +2 plus 1.5, that sign is positive, so it returns back +1. If x1 is -1 and at the same time x2 is +1, right? So that means one of them is +1, one of them is -1. +1 and -1 is 0, plus 1.5 is positive, and so sign of something positive is +1. Okay, that works. If they're both -1, okay, well, -1 times 1, -1 times 1, it's -2 when you add them together. If we add plus 1.5 for our x for this edge to that -2, it's -0.5. That's a negative sign, and so sign of that sum is going to be -1. Okay, all right. So that's our OR function. Again, I apologize for my brain hiccup. Let's take a look at the AND. And so the AND requires that both x1 and x2 have to be +1. If x1 is +1 and at the same time x2 is +1, that's a +2 when you add these two together. The +1 times its weight, the +1 times its weight, and +2 plus -1.5 is +0.5. If we take sign of that, that's +1, it's positive, and we get a +1. If both of them are -1, right, that's -2 when we add them together. We add -2 to -1.5, that's -3.5. Sign of that, it's negative, so it's going to return a -1. If one of them is +1 and the other is -1, well, +1 plus -1 is 0. So the contribution from x1 and x2 is 0 for our AND gate, and 0 plus -1.5 is negative, so sign of that returns back -1. Okay, and so in this case, we're looking at all the alternatives for the inputs we can have for x1 and x2, and x1 and x2 can be either +1 or -1. And so this configuration on the left implements an OR gate, and this configuration on the right implements an AND gate. And using that combination, these gates, these little networks, we can combine x1 and x2, our hypotheses, in different ways to get all sorts of labelings associated with our input representation. Does that make sense? Okay, so when we combine perceptrons, that gives us layers, right? We have our hypotheses, and we can now take these hypotheses and we can combine them to implement something that looks like exclusive OR, right? In the Boolean sense, but we're using +1 and -1 instead of 0 and 1. And so XOR, if you have two things, H1 and H2, two inputs, that you want to take the exclusive OR, you can build an exclusive OR by taking H1 ANDed with H2 bar, and then you OR that with H1 bar ANDed with H2, right? And so here we have an OR gate, and this OR gate is used to compute the exclusive OR between the output of hypothesis 1 and the output of hypothesis 2, where each one of these hypotheses can output either a +1 or a -1. Does that make sense? And so here in this circle, the multiplication of these two together represents the AND gate, the same AND gate that we see from the previous slide on the right. And this negation here is implemented by using a negative edge weight, right? And if you think about it, if it's a +1 and you negate it, then it should be a -1. You multiply by -1 edge weight and vice versa. Does that make sense? So here we have an exclusive OR between hypothesis H1 and H2. And you'll notice here we have this 1.5 on the X0 term, right? And we're combining that with a soft threshold. And we're basically taking hypothesis H1 and H2, and we're combining their +1, -1 outputs using an OR gate. And this is exactly an exclusive OR. And so in this picture, that's at a high level. And in the picture on the right, your right, we're actually expanding what these two nodes are. So we have this node H1 ANDed with H2 bar. That's over here. And then we have this node H1 bar ANDed with H2. That's over here, right? And so if we expand that, well, what is H1 ANDed with H2 bar? Well, when we AND, we have an X0 term that's -1.5, right? That's this first one, H1 ANDed with H2 bar. And then we have the H1 for the blue. That's H1. It's +1. And then we have H2 bar. H2 has a negative weight, -1, before it goes into that particular input. Does that make sense? And so that's an ANDing of H1 multiplied by 1 with H2 bar. Here's H2, and that negative edge weight on the blue edge from H2 to that node is H2 bar. Does that make sense? Okay. Likewise, H1 bar ANDed with H2, that's implemented in this lower middle layer node. And here we have H1 bar, so H1, that red edge, that's -1, so it's H1 bar. And here's H2, we're ANDing them together. Does that make sense? Okay, so that is the implementation of combining the two perceptrons H1 and H2, and we use -1 edge weight as a way of negating the output of a particular hypothesis. So then we can take our H1 and H2 definition, and we can expand that in terms of what H1 and H2 are, right? So we just said this output from this node is H1, and that's H2. Here we're combining H1 and H2. Here we're combining H1 and H2. Now these nodes, those are the raw inputs, and those raw inputs define what H1 is and what H2 is. Now, of course, X can be any value you want, a +1 or -1. And here we have our X0 term, which is fixed to 1. Sometimes in neural network literature, you'll see that described as the bias term. But nonetheless, it's fixed to 1, and each one has a weight vector. And here we have our x vector augmented with x naught, and then we have a bunch of weight vectors. And so the input here, that's W1 times x. Now we have a bunch of weights here, and his input here is W2 times x. And then we also have W naught times x naught, right? And we have a weighted sum of these, and this entire apparatus is our so-called feed-forward three-layer neural network. Now, on the left-hand side of this network, we have our inputs. That's our raw data signal. Now, these inputs could be columns from a table if you're dealing with data. They could be pixels from an image. It could be text from a document or what have you. And so we have our input, and then we also have what are called layers. These layers are these nodes here. So we have the first layer, the second layer, and the third layer. And the last layer, which is typically drawn on the right-hand side, is called your output layer, because that's going to be the output function of that hypothesis that is implemented by this entire network. So we have our input, we have our layers, and the last layer is our output. Okay, any questions about this? And so when we have a multi-layer perceptron through this feed-forward construction, it can do a lot more than a single perceptron, because you can combine these single perceptrons in interesting ways, and in doing so, you're realizing or implementing functions that are much more sophisticated. Now, of course, this is highly stylized construction. You'll notice here there are no links pointing from right to left. All the links are pointing from left to right. And there are no skipping of the layers. Now, in deep learning, you have skip layers, and it's a thing. But for this discussion for neural networks, we're just going to assume that there are no skip layers, right? Okay, and so if you think about it, this is a type of hypothesis, right? And depending on the setting of the weights, that's going to select a different stylized hypothesis. We have some weighted sum of some inputs, and they're put through a threshold function. In this case, it's a hard threshold, but it doesn't have to be a hard threshold. We take those functions and we weight them, and we put them into another set of functions through weighted sum. And so essentially, it's a composition of a composition of a composition of a set of inputs. And so this is a particular form of functions, and if you change the weight vector, you change the function in this special composition of composition function. It's a compositional function. Does that make sense? And so a neural network is nothing more than a particular type of hypothesis set, which is a composition of functions that are combined using weighted sums through some nonlinear threshold functions along the way. Okay? All right, any questions about this? All right, so why are combining perceptrons powerful? Now, certainly, if you have a nonlinearity, right, that changes the perceptron in 2 dimensions from a line on the plane to something that's curved. It can have arbitrary shape. But just even for a very simple linear model with no phi function, suppose you had the following target function, right? You had this polar arrangement of plus labeled points and minus labeled points. Now, with something like 8 perceptrons, well, you can't get a curved surface, but you can combine them suitably in a way that you basically approximate well this ground truth target function. And the more perceptrons you add, let's say you go to 16, the better and better and better you get in describing this sophisticated concept. But the problem then is that if you have too many perceptrons, you're going to have a lot more parameters. And with a lot more parameters, we found from our study on VC dimension and the VC bound, you pay for that. And how you pay for that is in needing a lot more data. And so oftentimes you can help by having soft thresholds instead of hard thresholds. And one of the benefits of soft thresholds is that it's smooth and differentiable, which makes it a lot easier to work with in terms of drawing curved surfaces, but also in terms of how you pose expressions for in-sample error. So this is a good thing. And one of the things you'll notice is that for a lot of publications on deep learning networks, you'll see that the data set is usually pretty large. And it's a so-called deep learning network because it has a lot of layers. It's a very deep network, right? And so by nature, the deeper you go, the more weight vectors you're going to have, and therefore the more parameters you're going to have, and the larger data set you need and number of in-sample points that you pay for in order to get good generalization performance out of sample. Okay? All right, any questions about this? Okay, so let's look at the following diagram. Now we're going to abstract away from perceptrons per se. And in this particular case, we're going to call the threshold function, we're going to call it theta. And so we said theta before was the sigmoid, but theta in general is just going to be some threshold. It could be the hard threshold, or it could be the sigmoid, it could be some soft threshold. And so here we have some input, and that input is a vector valued set of features in d dimensions. And again, we augment this d-dimensional feature vector with an x naught for a total dimensionality of d plus 1. And so we have our input layer, and then we have a set of hidden layers. The hidden layers are called hidden because they sit between the input and the output, right? You, as the user of a trained network, you see what's coming out of the output, and that's the value of your hypothesis h of x, and you specify the input, but you don't really see what's happening in the middle, right, as the user of a network. And so for that reason, they're called the hidden layers. Now, the hidden layers, if we look at that last layer, again, we said the output layer is that last layer, in this case, big L. And so big L is the right-handmost hidden layer, which is the output layer. And then we're going to use this index here, this variable lowercase or little l, to index between 1 and big L to correspond to our hidden layers, where big L, that last one, is the output layer. And so here we have our neural network, and each one of the edges connects the units from one layer, including the input, to the next layer, right? So here we have input layer weights, and when you refer to the weight vectors, these edges have weights associated with them, and these edges are considered layer edges for some layer. So in this particular case, we assign these weight vectors, these weights, to the layer that's just to the left of it, right? And so these are called input layer weights. These are called layer 1 weights, and then we have layer 2 weights, and so forth, right? Now, typically for the output, you don't talk about output layer weights. It's just an output, okay? All right, any questions about this? And so if we look at the hypothesis is really just, we take some weighted combination of the inputs, and you could pose this mathematically as W transpose X. And we have a different set of weights W corresponding to these red weights that go into this layer, into this node, or these blue weights which go into this node, right? And so here we have layer weights, and these layer weights are outbound from the layer before, and they're inbound to the layer at a given depth in the network. And so here we have a weighted sum of some inputs, and we compute a function over that weighted sum, our soft threshold or our threshold function theta, and then we take them, those outputs, so here's the first output, second output, third output, and so forth, and when we compose them through a weighted sum as inputs to another function. So it's really a function of a function of a function of a set of inputs. And again, an evaluation of a hypothesis is really just a composition, right? A composition of weighted sums of compositions of weighted sums of inputs once you get to the input layer. And so if we want to evaluate this hypothesis, what do? We present an input, we take our weighted sums, and we take those signals S, which is the same as saying W transpose X, for different weight vectors W, and then we compute our theta of that signal S. Does that make sense? So we keep doing that layer by layer in the forward direction from left to right until we get some final output, a single output, and that's our hypothesis h of x. Does that make sense? Okay. Let me check the time. 5:14. Already 5:14. Wow. All right. So I'm going to really kind of stay on this slide for a while because it's really important to understand mathematically what all these indices and subscripts and superscripts mean. Because when we get to the derivation of how you implement the weight update, it's going to be really important to understand what each thing means. Okay. So when we talked about a weight vector, we use the following notation. We say W superscript little l subscript ij. So the superscript L talks about the layer, right? So that layer number, little l, can index over the first layer, which is different from the input, the second layer, up to and including the output layer, which is big L, right? And so if we were talking about the network on the previous slide, well, here's our input. You could call it layer 0 if you wanted to. Some people do that. But we have little l is 1, little l is 2, little l is 3. We have a 3-layer network. Okay? So we have a weight vector, and our weight vectors are associated with a layer. Here we have the layer 1 weights. Here we have the layer 2 weights. Okay? Now you notice for each of these weights connect a particular input to a particular output. And let's take a look at what these inputs are. So when you have an input, that input, you'll notice, if we take this I is the input node, and you'll notice here this D is superscripted with L minus 1. So what does that mean? It says if I'm a particular layer at layer L, the things that input to me, that's from layer L minus 1. Does that make sense? So in layer L minus 1, the previous layer, you number those nodes. Let me show you an example. So here is a layer. Here's the layer before it. And the layer before it, it has nodes 1, 2, 3, but we start at 0 because remember, we augment with that x naught, right? That's our bias term. So if we look at the nomenclature, when we have a weight, it connects an input because that weight encodes a weighted sum. And that weighted sum is a weighted sum of the inputs into a particular node at a given layer. So here, this I says which input in the layer before from 0 through the dimensionality of that input are we referring to. Does that make sense? Okay. So the J term, that talks about the given layer L. And you'll notice here, D, that's a dimensionality, and it's the dimensionality of the Lth layer, right? And so that Lth layer has a dimensionality from 1 to D superscript L, and we use variable J to correspond to that particular node in layer L that we're considering. So if we look at Wij superscript L, we'd have the 0th input, the first, the second, the third, the fourth, the D superscript L minus 1 input from the previous layer. And that weight is going to multiply by each of those inputs from the previous layer with some weight value into the Lth layer. Does that make sense? Okay. So this is our Wij superscript L, and the particular Wij is the weight associated with the edge that connects the ith node from layer L minus 1 to the jth node in layer L. And L is the superscript as well. Okay. And so, does that make sense? Any questions about this? Okay. So let's take a look at what happens when you evaluate the signal. Now, of course, we have this nonlinearity here. And this nonlinearity is theta. It could be a sigmoid. It could be the hyperbolic tangent. There are lots and lots of soft threshold functions that are used. Now, you take that weighted sum. We often call that weighted sum S, the signal, right? And what does S do? S, it multiplies a weight vector uh, times the input from the layer below, and then it adds up all those weighted inputs to produce that signal. So if we look at what the signal is for a particular layer, we evaluate our soft threshold theta on the signal associated with the jth node in layer L, right? And so the signal for the jth node in layer L, if we were going to look at it, say here, well, this weighted sum is the signal for the second node in the second layer, right? And that's just going to be the weighted sum of all the inputs from the layer before, starting at 0, right? So if we look at this term, that signal, Sj, is a signal for the jth node in layer L. Now, what is that signal? All right. Well, that signal is the weighted sum, and you'll notice here that j is the same as the j for S sub j. Now, you take each of these I nodes input from the layer before, and you're going to compute the weighted sum. So you notice here we have the weights for layer L, right? And that is for node j in layer L. We're going to take the 0th, the 1st, the 2nd, the 3rd, the 4th, etc. For each of these weights from the input in layer L minus 1. Right? So that's kind of the fan-in that you're seeing when you see the diagram. And what are we going to take a weighted sum of? Well, we're going to take a weighted sum of the output signal, that's x sub I, the output signal for the node, the ith node in the layer before. So if we look back at the previous diagram, well, S, the sum, the signal, for the second node in the second layer here, that's the signal corresponding to this weighted sum for these red arrows. Well, what are we going to do the weighted sum of? Well, we have nodes 0, 1, 2, and 3 for the layer before, that's L minus 1, or the first layer, and we're going to take the weighted sum of this node times that weight, this node times that weight, this node times that weight, this times that weight, etc. Now, these outputs here from the node in the previous layer, that's going to be our x sub i's. X sub I, L superscript L minus 1. This is our x sub I, L superscript L minus 1. If this is layer L, well, the output of the previous layer, which is weighted by that weight vector, that weight is going to be the output of the layer before. Does that make sense? Okay, so we have our definition of this Sj superscript L, which is just the weighted sum. I goes from 1 to d superscript L minus 1 of wij superscript L times the output xi for each of the nodes in layer L minus 1. Does that make sense? Okay, so this nonlinearity evaluated on the signal for the jth node in layer L, once we evaluate it with this nonlinearity theta, we call that the output of the jth node for the Lth layer. So the output is nothing more than the nonlinearity evaluated on the signal, which is the weighted sum of the nodes in the previous layer. Okay? Does that make sense? Okay. So one of the nonlinearities that's popular, we talked about sigmoid, and sigmoid took the signal and it mapped it between 0 and 1 on the real number line, and we treated that like a probability in logistic regression. Another type of nonlinearity, our theta, is the so-called tangent or hyperbolic tangent. And what hyperbolic tangent does, it looks a lot like sigmoid, that kind of stretched out elongated S, but it maps the signal from the real number line to the interval from -1 to +1. Okay? All right. So this is our hyperbolic tangent. And when we want to compute our hypothesis h of x, what do? Well, we take our inputs, x, and you notice here, the superscript here is 0. Another way of saying the input layer is saying the layer number is 0, even though in the nomenclature, the layer number starts at 1, right? And so saying 0 is just a little cute trick for saying input, because the input is different from all the layers. So you notice here, if I have my x vector, and my x vector has some dimensionality, right? It has d plus 1 dimensions because I augment it with x naught, right? And so here we see the x, we say x layer 0, the first node, that's the first feature. The second node, that's the second feature. And then we have here uh, the uh, d dimensionality of the 0th layer, right? Which is just d plus 1, where d is the original dimensionality of the feature vector, right? So we take this and we input that into the first layer, right? And sometimes in the literature that's called the input weights. So you could call them layer 0 weights, a layer 1 weights, or you could call them the input weights. It all depends on what convention you want to use. And then we take the weighted sum, we compute our outputs, we take the weighted sum, compute our outputs, take the weighted sum, compute our outputs, and you propagate forward layer by layer until eventually you get a single output in the output layer, and that's the value of your hypothesis h of x. Does that make sense? And if you're using hyperbolic tangent, this h of x, because it's the result of computing hyperbolic tangent on some signal, is going to give you some output that's either +1 or -1. And in this fashion, you've implemented a classifier. Does that make sense? Any questions about this? Okay. So 525. Let's take a look at how you train this network. It's a special class of functions, and the special class of functions comes with it a special way of computing the weight updates that allow you to search through the space of hypotheses, looking for some hypothesis, working hypothesis, that best mimics the target function. So all of the weights that we have, and you can imagine if you have a lot of layers and you have a lot of dimensionality in the layers, you're going to have a lot of weights, right? And so effectively, you don't really represent all of your weights as a three-dimensional matrix or three-dimensional tensor, right? Because the dimensionality can be different for each layer. Some you can go from a very low dimensionality of D, and you can maybe quadruple or triple or multiply 100 times. You can have a fan out in dimensionality from one layer to the next. Or going from one layer to the next layer, you can have a fan in, meaning that the dimensionality or number of nodes in that layer gets smaller. In this case, we've drawn the network so that each one of the layers, you'll notice we have a dimensionality here, D. Here we have the bias term plus 3 nodes, bias term plus 2 nodes. You could have the same dimensionality, but that doesn't have to be the case. You could go from here, this could have been like 100 dimensions, 100 nodes, going down to 3 nodes, going up to 2,000 nodes, going down to 17 nodes, going down to 1, right? And so when you represent it, it's a set of arrays, if you will, or more correctly, matrices, that you use to represent the weight vectors associated with each layer. So it's a list of two-dimensional it's a list of matrices because the rank could be different for each layer. Okay, so how do you train this? You train this using something called backpropagation. And backpropagation is just based on chain rule for the partial derivative. And what your question you're asking when you compute backpropagation is you're asking for the partial derivative of the error at the output, h of x, out of that output layer, with respect to each one of these parameters, wij superscript L. Now, as you can imagine, this is absolutely a mess, because if you consider the composition of the weighted sum, composition, weighted sum, composition, weighted sum, composition, weighted sum, this gets very complex if you were to compute h of x, actually write it out in closed form. You'd have theta of weighted sum of something, which is theta of weighted sum of something, which is theta of, and then eventually you get an x input there. And so all of the weights that you have collectively, wij superscript L, this array of two-dimensional of matrices that correspond to the weight vectors associated with each one of the layers, every instantiation of this entire thing represents a unique hypothesis. And so how you search through this using stochastic gradient is you need to find the partial derivative, and then you're going to produce that update to each weight based on the contribution of each weight to the error, right? Now, certainly, if you were to do this directly, compute the partial derivative, it'd be an absolute mess. And so what backpropagation does, it's called backpropagation because it's a clever algorithm that does it incrementally by traversing the graph for the neural network in the reverse direction. And the beautiful part is when you first compute h of x by going in the forward direction from left to right, from the input to the output, you're going to get some values, the outputs of each one of these nodes, and you're going to reuse those values when you're going in the reverse direction, computing pieces of the partial derivative, taking advantage of the chain rule for the derivative. Okay? All right. So let's take a look at this. So we have our weights, and then we have the error, the pointwise error, on a particular example is pointwise error that we talked about. It's the error between the hypothesis evaluated on your input and the ground truth class label yn corresponding to that xn assigned by the target function. And so this is the error associated with a particular hypothesis. And so because a hypothesis is defined by w, this error is also a function of w, that large set of weights corresponding to that unique hypothesis. So what do we need to compute stochastic gradient? Well, we said we're going to take the pointwise error. So if we take our single input, x, and we run that through this compositional function to compute our output h of x, we can make this comparison between h of x's output and the ground truth label. And then we compute the partial derivative of that error at the output with respect to each one of the individual weights, wij superscript L, for all values of I, j, and L. Okay, any questions about this? All right, so here's an example about how we do it. Now first, motivate the partial derivative as a singular thing, and then talk about a fragment of the network, and then use that to move towards the chain rule that will ultimately allow us to do this piecewise in the backwards direction from the output layer, working our way back layer by layer to the input layer. Okay, so we want to evaluate the partial derivative of the error at the output with respect to each one of the weights. And we know that there's a linkage between the output error and each one of the stages, each one of the nodes or edges that we traverse when we go backwards in the network. So we have some output, and that output, xj superscript L, it could be the output layer or it could be some arbitrary hidden layer. Now this output is obtained by computing that threshold function, soft threshold theta, on some signal, right? So we say the signal, theta of signal is equal to that output. So there's a relationship between our output for a node and the signal over which we computed that soft threshold, right? So if we want to know ultimately the partial derivative of the error at some output with respect to a weight vector, we need to know how that weight vector is related to that signal, because that signal through that threshold is going to give us that output, right? And so when we take the partial, we want to say, when we say with respect to W, we're saying if you change W, how does that error change? And so error is a function of the difference between the ground truth and what is output. And if we want that connection, we need to apply that relationship in terms of the derivative going across that soft threshold. So we need the derivative of that soft threshold. What's another way to say that? Well, we need the partial derivative of the error with respect to that signal, because that signal is linked to the output, which is related to error, by this threshold. Does that make sense? Any questions about this? Okay, so now that we have that linkage to the signal, well, that signal is linked to the output that came before it. It's linked through this weight vector. And so if this output changes, this input into that signal changes, well, the signal is going to change, right? So we also want to know how that signal changes relative to that weight vector. Because that weight vector, if that changes, this input's contribution is going to change, which is going to affect the signal, which is going to affect that output. And so we need another derivative to account for that relationship. And so we have the derivative associated with the relationship between the signal and the output, and the derivative associated with the relationship between the signal and the input before it, which just happens to be the weight vector. So said differently, if we were to take the derivative, we say that the derivative of the error with respect to the weight vector in layer L, Wij superscript L, is the same as the product of two things. The derivative of the error with respect to the signal at node J at layer L times the derivative of the signal at node J layer L with respect to weight vector Ij at layer L. Does that make sense? Any questions about this? Okay. So, yes. Okay. And so literally, we're taking the partial derivative. We want the derivative of the error with respect to this weight vector. But this weight vector is linked to that error first through the signal, and then from the signal to the output from that node. And how we decompose it, now you could take the expression for h of x, and it would be an absolute mess, and just compute that derivative directly. But you're going to need chain rule to do it because it's a compositional function. And in this case, we're taking the relationship as to what values contribute to another value. Because if some value is a function, if I contribute to that error, well, I have to make some adjustment for that error to change, right? And that's exactly what the chain rule is doing, is decomposing it in stages based on those relationships. And so the output is related to the signal through this nonlinearity, and the signal is related to what comes before it through this weight vector. And this weight vector is exactly what we want to know as we vary it. How does error change? Okay? All right. So, and I'm going to end with this thought. It's already 5:36. So we have this expression for the chain rule. And let's look at each one of these terms separately. Because if we multiply these two terms, we get exactly what we're looking for. And so let's look first at this term here on the right-hand side, right, this multiplication. We have the partial of Sj, the signal at node J in layer L, with respect to the weight vector Wij superscript L. Now, of course, if we take the derivative of this signal Sj with respect to that weight vector, Wij, now remember Wij superscript L is only a single weight vector. So we're going to have a weighted sum composing that signal Sj superscript L that's going to have other weight vectors that are not Wij superscript L. But when we take the derivative with respect to Wij superscript L, everything that doesn't involve that weight vector, it drops out to zero, acts like a constant. Does that make sense? All right. So here, the only factor that depends or has that Wij superscript L is going to be that one that multiplies xi superscript L minus 1, right? Because that is the input on the other side of that edge that contributes to Sj, right? So if we take this derivative, what does that give us? Well, what that gives us is xi superscript L minus 1. Because we have xi plus 1, xi plus 2, xi plus 3. Those don't involve Wij superscript L. So they look like constants. You take that derivative, they all go to 0, except for that one term. Does that make sense? All right. So the next thing that we need is we need this part. We need that partial of the error with respect to the signal. Now, we're just going to give this a name, and we'll pick back up on Thursday with how we get that. That's going to be called the delta. Now, this delta is going to be the derivative of the error with respect to the signal. And you will see next time that this delta involves the derivative of this nonlinear function theta, this soft threshold. Does that make sense? Okay, and what we'll find is that in order to calculate this delta, we're going to need inputs, these xi's, right? But we get these xi's as a consequence of evaluating h of x in the forward direction. Absolutely beautiful construction. Does that make sense? Any questions about this? All right, so we will pick back up with this. It's now 5:39. We'll pick back up with this on Thursday, and we'll go into how you get these deltas and what pieces of information are available when, and go forward with that. Now, it's interesting that a matrix is a tensor is the generalization of a matrix. A zero-dimensional tensor is a scalar. A one-dimensional tensor is a vector. A two-dimensional tensor is a matrix. A three-dimensional tensor is a 3D, like a cube of values, right? And so have you heard of something called TensorFlow, right? TensorFlow is a graph-based system that's used, it's very popular, for computing iterations like this for backpropagation. And so if you think about it, I said every set of weights is a matrix. A matrix is a 2D tensor. And so the set of weights for a particular layer, that's just a matrix. And that matrix is the dimensionality of this by the dimensionality of that. And so the tensor part comes from the fact that when you're computing these signals, you're literally multiplying matrices times vectors. And so you're computing tensor products, the multiplications, and then the flow part is the fact that you're taking that result and you're sending it to another node in the graph that then computes another tensor operation. So TensorFlow is nothing more than a graph-based system for propagating partial results from doing matrix or tensor operations. Okay? And that was what was developed by, well, Google popularized it, but the idea of tensors is a very relatively older concept. But TensorFlow is a framework for doing that, and it works really well because you can lay it out on distributed systems to speed up your computations. Okay? All right. So with that, any more questions so far? So we'll pick back up with this on Thursday and finish up the module on how you get these deltas and how you put that together with a forward pass and a backward pass to give you these updates for backpropagation. Okay, so I will see you all on Thursday.